Hey, good afternoon, everyone, and welcome to today's SANCOLD Young Persons Forum webinar. My name is Ashley Kutsia. I am the YPF chair at SANCOLD, and it is my pleasure to host this session on a critical topic in water management today. How big is your dirty water dam, or how big should it be? A special welcome to our speaker, Gerald de Jager, a highly respected expert in water resources planning with over 25 years of international experience. His expertise includes hydropower planning, water resource system operations, climate change adaptation, and risk-based water allocation. He is a key contributor to technical training and capacity building, sharing his knowledge with institutions, universities, and professional bodies across Africa. In addition, he serves as a co-opted management committee member of SANCOLD and represents South Africa on SANCOLD's Technical Committee F on engineering activities with the planning process for water resources projects. Gerald, we appreciate your time and look forward to your insights today. Before we begin, I would just like to go over a few housekeeping points. Your mics and cameras are muted during the session, but you are welcome to raise your hand at the end during our question and answer session and type any of your questions during the presentation in the chat. This session will be recorded and will be made available afterwards. All right, thank you so much, Gerald. The floor is yours.
Well, a good afternoon to everybody. Thank you, Ashley, very much for that introduction. It's great to be back. We did some webinars in the past and I think really successful one last year that you guys hosted. So thanks for all the work that the YPF is doing. It's important and we support you and we're all grateful for the effort you put in there. And also for convincing like me to give up a bit of time to chat to everybody. And I think there's quite a large crowd that logged in today. So that's great. Very big welcome from my side as well to everybody on the line here. Please contribute to the discussion at the end, as Ashley said. I'm going to share some ideas here. These are not rules or fixed or written in stone or anything like that. I'm sharing ideas with you as a bigger community with the intention of facilitating discussion and hopefully ultimately for us all to be able to do a better job. So what we're going to talk about today is really important, dirty water dams. And in particular, how big should that dam be? Now, maybe the process of finding out the sizing your dam or operating your dam is perhaps not quite as simple as some people think. So I want to shed some light on that this afternoon. And as I said, facilitate some discussions at the end there. So what we're going to do first, just quickly look at legislation to help us understand from that perspective, what is actually defined as a dirty water dam? How are we supposed to size those? What are the criteria? And then also some helpful hints and guidance from the legislation on actually how to achieve that. But we must take the time to read these things and make sure that we are familiar with them so that we can do the right thing. That will be followed. I'm going to talk to you a little bit about water balance in terms of dirty water dams, and also how to do continuous modeling as opposed to event-driven modeling. So this idea of continuous modeling, and then also the use of stochastics. Because at the end of the day, I mentioned this word stochastics now, this is all about risk management, the risk of things like contaminating the environment. So we must follow a risk-based approach to address this problem. And that's what I'm going to talk to you about today. It's going to be very basic, show you some good stuff. And as I said, please contribute and tell us what you think about all of this. So with that, let's move on. Legislation then.
Gerald, you need to share your screen. Sorry.
Of course.
I'm not sure it's not being shared at the moment.
You and I spent so much time on figuring out how to do that, and I haven't. So my apologies to everyone. Let's try that. Okay, there we go.
Thank you.
So that should come up. Thank you for telling me. So you can see the nice photo. Thanks to DWS for this photo. It's not mine. So that's the plan. Let's move into the first part of the discussion, which is on the legislation. The first and very important, obviously, is the National Water Act of 1999. There's a lot of stuff in here that relates to what we're talking about today, but I wanted to highlight just a few things for you in there, and for you to maybe at your leisure go back and read up on this a little bit more. I think what was important here is to actually define what a dirty water area is. So you'll see that it is shown here. I just want to create a laser pointer here. Dirty area, any area at a mine, and importantly, or activity. I think what they're suggesting there, it doesn't have to be a mine necessarily. Any such activity that causes or is likely to cause pollution of a water source. So that's important. So it's not just mines, it's other things as well, industrial activities, even agriculture, whatever the case may be. So does it apply to what it is that you are doing? That's what you need to consider. And then what is a dirty water system? Includes any dam, other form of impoundment, canal, works, pipeline, residue deposit, and any other structural facility constructed for the retention or conveyance of water-containing waste. I think that's important to realize as well. These are not necessarily dams, and certainly not necessarily dams that operate in isolation. It might be a system of dams. There might be water being transferred from one part of the system to another, and ultimately there may be the potential for spill from one of these facilities into the natural environment, but it's a system specifically. Now, for the purpose of our discussion today, I'll focus on just a dam, but please remember this context, that it is not necessarily a single dam that we are talking about. So those are some of the definitions in the Act. Next, we have the actual criteria. Now let's read this one carefully here. The capacity requirements of clean and dirty water systems. Now, it talks about clean water systems here as well. What's interesting there that I haven't highlighted, but it's maybe to take note of, there's also a limitation on the likelihood or risk of spill from the clean water system into the dirty water system. So maybe take note of that one, something that you may have missed in the past. But then I want to get down to this yellow one that I think many of you know and are familiar with. But we're going to read these words carefully. We must design, construct, maintain, and operate. Do you see there? So it's not just the sizing of the dam, it's how do you operate the system at a mine or activity so that it is not likely to spill into the clean water system, which includes the environment, right? More than once in 50 years. So they don't want a frequency, it to happen more frequently than that. And in the process of designing, constructing, maintaining, and operating your system, you must be able to show that you've done what is required so that you can claim that you will adhere to this criteria, not spilling into the environment more than once in 50 years. What does once in 50 years mean? We're going to chat about that a little bit today as well, obviously. But if you're more familiar with things like annual probabilities or annual risks, a 1 in 50 year event on average would be the same as saying the likelihood of it happening in any given year is 1 over 50 or 2%. So what we're chasing is a likelihood or a risk of spill of less than 2% in any given year. I'm going to leave that up there for another second so you can familiarize yourself. By the way, that I do actually make notes here of which section it is that we're referring to, so you can go back and have a look at that when you have a moment. Okay, the next one I want to talk to you about is the best practice guideline A4 for pollution control dams. This is the old Department of Water and Forestry 2007 publication. This one is really useful because what it does is it helps you adhere to the stuff that we've just seen in the Water Act, but what are the actual processes? What is it that you're supposed to be doing to achieve this? So if you don't have a copy of this, please make sure that you get one. If you don't know where, then let me know. I'm happy to share the one that I've got. I got a new copy from Louis Hutton today. Louis, if you're on the call here, thanks for giving me that one. Mine was lost in a theft, but that's a different story. Right, so pollution control dams. In the guidelines, I want to show you some of the good stuff in here. Section 643, hydrology and stormwater. Now, I need you to focus in on this quite well, because what I want to do is differentiate between two things that you see in here. Do you see here the first point that it says the spillage frequency depends, this is important, on the size of the dam, but also other things. That's something that is important to understand. if I have a high abstraction rate from my dam, for example, it would likely be running at a lower level, and therefore the risk of spill would be smaller. So it's not just the size of the dam, it is also the way that I operate the system. Now, what they say here is very important, this underlined word, initial designs and dam sizing can be computed based on something like the 1 in 50 year runoff volume. But that is the initial design. You can't stop here. You have to move then into a process where you confirm the dam size based on the spillage frequency, and that you can only really determine by means of continuous modeling. And it says so here, very explicitly. And when you do that, you must account for all of these things here. You see, they list them. They're talking about all the things that can add to water volumes in the dam and the things that will make that reduce. So you've got rainfall, you've got evaporation, you've got abstractions, you've got infiltration and other losses and evaporation. All of that must be accounted for in your model. Another thing that I wanted to point out here, and sorry, I'm nearly done with the legislation. This is sort of the boring part of the discussion, but it's important that we go through this. The water balance will be used to specify a minimum storage level. Now, this is important. That's that level you want to keep your dam at, and it is to ensure that you've got adequate freeboard, as it says here, to maintain so that the stormwater inflow can be accommodated. So that's the stormwater inflow component. You must be able to accommodate that, but this is important. And the spill frequency is met. Those are not the same thing. Okay, so please differentiate in your mind between these two concepts. The one is to facilitate, accommodate the stormwater flow, and that is an event. And the other one is over the long term to meet the spill frequency criteria that we spoke about before, that maximum 2%. Okay, and this is really good. I was so glad to see this in here again. It says it is important to consider that in general, it is not the single events that results in spillage. So that big rainfall event, it's not necessarily that thing that causes the spillage, but rather, let's say, a prolonged period where it is wetter than usual. You know, in that case, you can imagine that if your dam, if it's wet for a long time and your dam starts filling up over time, it might take a fairly small event to cause it to spill, right? And if you look only at storm events, you will miss those spill events. And I think you will find that if you follow only this approach at the top here, you might end up missing potential spill events in your modeling and therefore potentially undersizing your dam. I just wanted to bring this up again. It's a very useful little technical box that's also in this guideline here. They talk about using rainfall. They also talk about using stochastic rainfall. So I'll show you some of that today. And they also talk about modeling all the things that are important in terms of the behavior of your dam, including, if it is applicable, rainfall runoff. And they mentioned some models here. ACRI is a well-known South African model, the UKZN. Why is it important to understand the rainfall runoff response? Well, again, similarly to the sort of things that we discussed a minute ago, for example, if it's been raining for a while and the catchment, even if it's small catchment, is wet, then a small rainfall event might result in a lot of runoff and a lot of that runoff ending up in your dam. Okay, so what is this story with water balance modeling then? If we need to do water balance modeling, we must understand how that works. Now, the guideline again is very helpful in it guides us on how to do these things, and it has this little diagram in there that explains how the things that we would need to consider when we model the water balance of a dam like this one. Now, some of the things we would probably almost do intuitively. It would be easy to remember. You know, obviously, you've got water that's sitting in the dam here. You've got rainfall onto the surface of the dam, and that must be considered as, in inverted commas, an inflow. But we've also got evaporation from the dam surface here. So that causes an outflow of water from the dam. There might be seepage, unless obviously it's a line dam, in which case that seepage should be negligible. We could have abstractions from that dam. Our model must allow spill when the dam is full at the full supply level. And then if there is a catchment, we must model catchment runoff. If there's seepage, We must model that. And then it says here mine workings, dewatering, but really any water from the process that is fed into this dam must be taken into account. And then what it doesn't show on here, but all the operating rules around these things that we want to model. How do we want this dam to be operated, and how do we want it to behave? I just wanted to highlight one little thing here, that is in the actual impoundment basin of the dam, this area here, if you like. When the dam draws down, obviously the surface area, the exposed surface area, the water in the dam will reduce. That area will reduce, and our model must account for that. So the rainfall onto the surface area of the dam will reduce accordingly, and so will the evaporation. But because that area of the water reduces, that little area in between, so it's below the FSL but down to the level in the dam, that creates, if you like, a little portion of additional catchment where runoff would also occur. So we must also remember to include this in our model when we model the runoff going into the dam like this. I'll leave that on there for a second for everybody to have a look at. Write down your questions. Okay, so now we come to a classic slide of mine, and I always have to apologize when I show people this slide. I know this doesn't really look like a dam. It looks really weird. So I got so excited about doing the animation on the slide that I messed up the dam a little bit, and I always get sort of called out for that by the dam engineers and other people. So my apologies in advance. I know that's not what a dam looks like. But what I want to show you is in principle how these water balance models work. And they all work like this. Essentially, it does a balance of my dam, the thing that I want to model here. I can pick the time step of the model. The guideline actually prescribes at least a daily time step. Why a daily time step and not a monthly time step? Well, in terms of the operation of these dams, generally that would happen at a much finer frequency than a month. So that would be the advantage of doing daily modeling. And these events, these large rainfall events, also could happen on one day or a number of days, and we might lose that if the granularity is not appropriate. So generally, we use a daily modeling approach. Now, how this balance works is what these models typically do is they calculate the change in the volume of water in the dam, delta S, is equal to inflows minus outflows. And that's literally as simple as it is, but assuming that you account for all the things that cause inflows and outflows to the dam to happen in that given day, the sorts of things that we mentioned before. Now, if on that given day, inflows are smaller than outflows, what we'll find is that delta S is positive, is negative, in which case the dam will draw down. This is the animation that I talked to you about, but I will, someday I'll improve the slide. If alternatively, inflows are small, inflows are greater than outflows, delta S will be positive and the dam level will increase. And if that situation persists, the dam will ultimately spill like that. So some more animation for you to enjoy. So this is in a given time step. So this is how the balance works. But how do we take this concept and apply that to what we call continuous modeling? So what happens if this sort of thing happens over and over and over again over a long period of time? Well, the principle is actually pretty simple. If in the first time step, we know the start storage in the dam, we can then calculate the change in storage over that time step, and therefore the end storage for that time step, in this case, time step 1. And I know this is really obvious and simple and straightforward, but the key to the whole thing is that the end storage of this time step then becomes the start storage for the second time step. And applying this approach over and over and over again, we can solve time step after time step from the very first time step to the last time step over whatever period of analysis that we would like to undertake. And that would be this sort of thing. It's very simplistic. It's just to show you in principle. But let's say, for argument's sake, that these are the inflows or the flows into a dam, and this red line are the flows out. Then we know the volume of storage in the dam at the start of the analysis. We can then apply this water balance approach to solve levels or volumes in the dam over the entire analysis period, and might end up looking something like that, where the dam draws down, the dam fills up again, and it spills when it's full, and so on. What you will notice is if I take that red line and I plot it on the blue line, in the cases where inflows are smaller than outflows, the dam will draw down. And in cases where the opposite is true, the dam will fill up. And obviously when it is full, it will spill. And this is fundamentally the principle of a water balance model we use to do continuous modeling. So let's look at a very simple example system. The example we've got here, we've got a dam at the bottom there. It's got a little catchment. There's water. There's obviously a bit of runoff from that catchment that can flow into the dam. There would be evaporation from the surface, the exposed surface area. There would be rainfall directly onto the surface. Remember that incremental little catchment I spoke about? There might be water pumped into and out of the dam, and maybe water pumped from this dam to an upstream dam, whatever the case is. And some of the water here might be used for something. For example, at some of the mines, some of the coal mines, they might use water in some of these dams for things like dust suppression, whatever the case is. But that may be what the dam looks like. We must consider, when we model this, all the relevant infrastructure and how they are linked, and also how the system is operated. The things like, for example, control levels in my dam. So if it reaches X level, this will happen. When it spills, that will happen, and so on. We can consider all of these things in our model. Now, you can imagine if you look at this sort of example, which isn't really even that complicated, but you would never be able to do simply a flood hydrological analysis to be able to figure out what the likelihood of spill is in that dam. I mean, this is way too complex to be able to do that. The only way that you'd be able to do that is to do continuous modeling using a water balance model. So this is an example then of the output of a model, this sort of model that we're talking about, following exactly the approach that I just explained, where we have some start storage, we know inflows and outflows for each of the days in the analysis, and then we can model the behavior of this dam over a long period of time. This particular example is 76 years based on the historical hydrology. So that would be historical rainfall, evaporation, runoff, and all of that on a daily basis, analyzed over a 76-year period. And this is what we find. If we pick, in this example, a volume of 20,000 cubic meters, that is plotted over there, you can see that the dam does every so often actually fill up and reach the full supply level. And in each of those cases in our model, that would result in a spill event. Now, clearly, if we look at that, intuitively, my gut feel tells me this dam will probably not comply with the 1 in 50 criteria, or the 2% spill frequency criteria. So the beauty of having a model like this is I can then very easily go back to the model and do a second run where I test a different size dam. So what would happen if my dam is not 20,000 cubic meters, but is some bigger volume? And I can then do that and see how the dam would behave in that case. So this is for a 30,000 cubic meter dam. You can see the difference. I'll just toggle between the two there. That's the 20,000 with its spills and the 30,000. And you can see that by increasing the size of the dam, I've reduced the number of modeled spill events. I'm going to show you again, 20,000, 30,000. So again, I might want to test an even bigger dam, see what that would do. And there, the 40,000 dam has no model spill events over this historical analysis period. Just to clarify, when I say historical analysis period, what I mean by that is that I use the historical hydrology, but the dam and all the things that interact with that dam are at a fixed development level. So it's historical hydrology results in this. So let's want to go back and show you all of them again. So that's the 20, the 30, and the 40. Now, the problem with an analysis like the one I just showed you really fundamentally is the fact that I was using only historical hydrology. If I go back to that picture, if I analyze this dam for these 76 years, that is what it came out at. That's the resulting behavior of the dam as I model it. The problem is that, however, hydrology is fundamentally uncertain. We can't predict exactly what the weather and the rainfall is going to look like over any other given period. Even if you ignore the impact of climate change, which is something we can discuss at the end, but even ignoring that, if I analyze this dam, everything that's in here in exactly the same way, but somehow could do that for the next 76 years, I would get a different answer. The problem, however, is that I don't know what the next 76 or whatever the period is that I'm interested in. I don't know what the hydrology looks like in that next period. I know that it will be something somewhat similar to this hydrology. It's still the same catchment, still the same climate, and so on. So it will be similar, but it will certainly not be identical. And because it is not identical, you will find that in any other period, the likelihood of a spill will be different from the historical period. Now, with that challenge in mind, we cannot use only historical hydrology to do this sort of analysis. Because remember, ultimately, we want to quantify the risk of spill. And we don't know the risk of spill in any other period based on only this period's hydrology. And hence the need to use stochastic hydrology. I know that there are some individuals that are not pro using stochastics. I've heard many arguments. One argument that I've heard is that stochastic hydrology introduces more uncertainty into the analysis. My counter argument is that that uncertainty is actually already there, like I just explained. We use the stochastics to try and quantify that uncertainty so that we can actually quantify the risk. So we need to use stochastics. If I'm honest with you, I use a lot of stochastics in the work that I do. It adds a lot of effort, as you can imagine. And with additional effort, there's additional scope and there's additional cost. That's unfortunately how it works. But we have to use the stochastics so that we get to results that we can trust and apply practically. So what do I mean by stochastics then? Here's a bit of a summary. We can generate hydrological sequences synthetically. What's important to understand is that sequence of hydrology, the stochastic sequence, did not actually occur. And it's essentially almost impossible that it would ever occur. But the point of the stochastic sequence is that it could occur in the catchment that I'm analyzing. It is realistic and plausible for this particular catchment. How do we achieve that? Well, there are lots of stochastic models out there. We've got some locally developed ones as well. If you're interested in stochastic models, then you can chat to me afterwards and I'll give you some guidance and advice there. But very important, the ones that we use locally are based, that they do an analysis based on the statistical characteristics of the historical hydrology. So it's not random. It's based on the known characteristics of the hydrology in this catchment. It uses those characteristics then to generate statistical distributions that fit the historical hydrology, and then use that as a basis to generate the stochastic sequences. Now, each of these sequences would have a similar look and feel, if you like, to the historical one, but each sequence would be unique. And also, each sequence would be equally likely, if that makes sense. So they're statistically independent, but all of them are unique and equally likely to occur in our catchment. And each of them must be plausible show you just a few examples of that. These are stochastic runoff sequences. In this case, we can similarly generate stochastic rainfall sequences and use them to generate stochastic runoff using a rainfall runoff model. You can see here what these look like. This is runoff in cubic meters per second over some days. And the sequence at the top is actually the historical sequence. Now we can generate however many sequences we like. There's no limit really to how many you can generate, but this, just as an example, is what sequence 24 looks like. If you compare the two, you'll see that they do look similar. Maybe this one is a few more sort of drier periods, like that one there and that one there. But in essence, the same sort of look and feel as the historical one. And then sequence number 499, these are just examples that again looks very similar to that one. Maybe we wanted to higher peaks there, higher runoff events like that one over there. Each of these sequences in my example is the same length as the original historical sequence. So what we can do now is, instead of analyzing only the historical sequence in a water balance model, we can take each one of these sequences in turn and analyze the same system using the stochastic sequence, if that makes sense. So if we analyze the historical sequence, we will get a result. If we analyze the same system using a different sequence, we will get a different result, and so on, all the way through to the last sequence that we analyze. And the result might look something like this. This is, for this particular example, what we analyzed was a dam of size about 50,000 cubic meters. Using all the inputs and outputs, as I explained, we put it into a water balance model, and we model the behavior of the dam over a period, the 76. This is the historical one. You can see clearly that in this analysis, the dam is modeled never to spill. That's the full supply volume there. And the highest volume modeled here is just under 40,000. So this dam never spills. However, same dam, same system, same model, everything, but using a different stochastic sequence, you can see how significantly different the result is. This is the modeled output using sequence 24. And then similarly using sequence 499. And you can see here that indeed, clearly, we have an event there where the dam fills up and will spill. And I want to reiterate, across these three examples, nothing changed except the hydrological sequence, the stochastic sequence that we use as a basis to model this dam. So there's your spill event. So now you can imagine that if we analyzed our model or analyzed our dam using this sort of approach, but not just 1 or 2 or 3, but let's say 500 sequences, that would be pretty difficult to understand the results, because you would have 500 lines like these plotted onto one set of axes, and it would be impossible to figure out what is going on there. So to get around this problem, we like to show our modeled results as a probability distribution. There's different ways of doing that. What's commonly used is box plots, box and whisker plots. You may be familiar with those. For the purpose of this discussion, what I've done is I used colored bands like this to show different exceedance probabilities. Essentially, sort of bluer colors, there's a smaller likelihood that it will go down to that level, and a smaller likelihood that it will go up to the level at the top here. These are actually exceedance probabilities. Maybe better, easier to understand if you see it on a graph. But the black line in the middle there representing the median at any given point, the maximum, or if you like, the zero exceedance probability is that dashed line, and the 100% exceedance probability is this dashed line. Now, this is what that result might look at. I'm going to give you a moment just to look at that and internalize it all. Basically, what you're looking at is these colored bands. How that was generated is what we would do. We would model this dam over in this case, 76-year period using sequence 1. and then using sequence 2 and 3 and 4 all the way to sequence, in this case, 500. And then on any given day, remember this is a daily analysis, so on any given day, we would look at all the results for that particular day, all the modeled volumes in the dam for that day, find the median, find the 25 exceedance probability, and so on, all the way through to the 0 exceedance probability, and that would give me my distribution, probability distribution, as you see here. So this is suggesting that the dam, if you look at the black line, which is the median, the dam is likely to be moving along here, but there is a possibility that it will be as high as that or even as high as that, but the probability reduces, as you can see, in terms of the probability distribution. I hope that makes sense. If it's the first time you've seen a graph like this, it might be really confusing, but I'll give you a moment to have a look at that. Okay, so once we are at this point, we still actually don't know what the spill probability is. Because what we're interested in is an annual probability of spill or an annual risk of spill. And this doesn't really show us that yet because this is a daily graph. And I'm interested in the probability of spills on an annual basis. I'm trying to find that 2%. And I'm trying to size my dam or operate my dam so that I don't exceed that 2% annual spill probability. So the way that we do that is we use a fairly standard approach to calculating the spill probability, but on an annual basis. And I want to show you how that works. Let's say, for argument's sake, that I've analyzed in this way, in exactly the way that I've just explained, n years, whatever they might be, 70 years, 50 years. You want it to be as long as possible, not 20 years, maybe 30 years, 50 years, 50, 60 years, 70, as long as you can. You've analyzed n number of years from that day through to that day. And we've done it using stochastic inputs. So stochastic sequence number 1, we've analyzed that for, what is this in this case? Let's call it 76 years. So sequence 1, we analyzed for 76 years and we checked, do we have spill events? No, we don't have spill events all the way through to here. Then we go back to the start and we analyze sequence 2 in the same way. And now we see, hang on, here we do have some spill events. And then we do that for all the sequences all the way through to the last sequence. And again, we check whether we have spill events. What we then do is we check, is this a spill sequence? And what I mean by that is, does this result contain any spills? And in this case, we can say sequence 1, for example, is no. Sequence 2 is yes. And whatever the other sequences is, we would check how many sequences contain spill events. And we call that a spill sequence. But remember that sequence is 70 odd years long. So in that entire sequence, if there are, it's pretty unlikely that there will be no spills because it's over a very long period of time and so on. So once we know that, once we know how many years we've analyzed, we know how many sequences we've analyzed, and we know how many of those sequences resulted in spill events, we can then go through, count the number of spills, and go through to this slide that people that have been exposed to what I do may have seen a lot of this in the past. But it's basically a statistical approach to calculating the annual risk of spill. Let me take you through this quickly, and you might not catch all of it now. It doesn't matter. Sometime down the line, if you want to know more about this, I'm happy to share more. But basically, what we can calculate is the risk of spill over any n-year period, where n is the length of a sequence. In this case, about 70 years, right? So any given sequence is about 70 years long. What is the risk of spill in a 70-year period? And we calculate it like this: the number of spill sequences that we've counted divided by the total number of sequences analyzed. And that gives us the risk of spill over an n-year period The opposite of that would be the probability of no spill in an n-year period, which is 1 minus that number. Then we can calculate the recurrence interval of spill events in years. Remember here, we don't want them to be more frequent than 1 in 50 years, as per the Act. We use this weird looking equation here to do that, where n is the length of a sequence. So you can see how the length of the sequence comes into it here. I'm not going to explain to you how we derive this equation, but I do have that on a slide if there's someone that's really interested in the statistics behind it. It's not difficult to derive. But very importantly, then ultimately, we can calculate the annual risk of a spill event, which, as we said, should not exceed 2%, as per the Act here. And this is then the equation we use to calculate the annual risk of spill, using a robust stochastic approach and continuous water balance modeling. Now, the great thing about this approach is the following. It's more than one great thing, but this is one of the great things, is now that I've got a model set up, I might find that the spill event I calculate does in fact exceed 2% for the dam size and the operating regime that I've chosen. I might find that that 2% is exceeded. The beauty of having a model now set up is I can change anything in that model, rerun the whole thing, recalculate the spill probability, and do that iteratively in a scenario approach until I get a configuration that complies to the criteria. Does that make sense? Okay. So I thought of just bringing this in here. For some of you may have seen me talk about this at some of the earlier SANCOLD conferences, and we published a paper on this. The question arose when and this is Louis Hutting and I sort of talking about this sort of modeling approach and what is good and what is not and so on. And the question came up, how many sequences should I actually analyze? Now, in the example that I showed you here, the approach here to generate this plot was to analyze 500 sequences. But it's then that Louis said to me, but why 500? How many sequences would be enough? Now, I don't think it's an easy question to answer, but what we ultimately decided to do is to analyze a system using a different number of sequences each time to see, as we increase the number of sequences we analyze, do we find that the results converge into something that makes sense, right? So if you analyze a very small number of sequences, we expected that we would get sort of results all over the place, but that as we increase the number of sequences, that ultimately we would have enough that adding more onto that would not really change the result significantly. That was the sort of approach that we took. And this is what we found. It's similar to the plot you saw before. This is the model dam behavior for that same example, 76 years analyzed, in this case using just 10 sequences. And that's the result that we got for only 10 sequences analyzed. So we still have a probability distribution, but it looks very different to the one you saw before. And what I want to show you now is we reanalyzed and reanalyzed, in each case using more and more sequences. And I'm going to show you what the plots look like as a result of that. So this is for 25 sequences, up to 50 sequences, 100 sequences, 150 sequences, and sort of start seeing it stabilize a bit now. 250, 300, 350, 400, 450, and 500. And you'll see that the difference between, there is a slight difference between 400 and 500, but it is not massively significant, I don't think. But we wanted to go one step further, which is to then use these results to quantify the spill probability in each case using the approach that I just explained with those equations. And this is the result that we found. So remember, we are targeting not exceeding the 2%, which is highlighted here. And there's the result that we find. So this is the number of sequences analyzed and the annual risk of spill that we got from that. You can see that it's all over the place for a small number of sequences. And then it starts to sort of do this sort of thing down to about 500. Now, I'm not saying that if you analyze 600, you won't get a different answer. You may well do. But I think based on this, it appears that the thing seems to be stabilizing over here somewhere. And based on that, we made a recommendation that you run at least 500 sequences for this sort of analysis. However, I have to qualify this was in a particular case for a particular type of hydrology in a particular place in the world. So this will be different elsewhere. So this is certainly not definitive, but at least we made a start on trying to understand these dynamics. As a final point here, in the presentation, actually, I just wanted to mention to everyone the importance of monitoring. I'm just going to show this slide here again. I mean, you can imagine that if we didn't know anything going on in the system, for starters, it would be very difficult to even put anything into a model without ending up doing a lot of guesswork and making lots of assumptions. So we need to understand what's happening in the system to be able to model it in the first place. But in addition to that, once we have modeled it, we decided on operating rules and criteria and things like that. If we don't monitor the behavior of the system, we wouldn't know whether our approach is working out there in reality. We have to monitor the behavior of the system. That would be things like water levels and things like volumes of water pumped into and out of a dam and things like that. All of these things actually need to be monitored. You can imagine almost anything that would affect the balance of the water in the dam needs to be monitored. With the understanding, obviously, that there are bodies in South Africa that do things like rainfall monitoring. But I think it's important here to just stress again the importance of monitoring and how without that, it really would be very difficult to manage the system in any reasonable way that corresponds to the way that we modeled it. Because remember, the way that we modeled it ultimately would be the basis of the recommendation. So the assumption would be that the operations follow that approach. So actually, this is in conclusion, but it's not the end of the presentation. I wanted to just show you an example of a water balance, an actual water balance model for a second. But before we go there, just quickly then in terms of conclusions, I'm going to give you some time to have a look at that. But I think it is important, and I tried to make the point here that we have to use continuous stochastic daily water balance modeling to quantify and assess the risk of spill. We cannot only use, for example, floods or events that cause high inflow or high rainfall events. We have to look at continuous modeling in this way. And then we can use scenario analysis to assess all of these things dynamically, because that's the way that it works in reality out there. We did find that the results depend on the number of sequences, and we suggest something in the order of 500, actually, or more sequences. I might want to change the wording here a bit, 500 or more. And then lastly, the monitoring is critical. We can't manage what we don't know. So, there's a final one. This is actually important. I'm glad I've got the slide on here. The SANCOLD as a body are currently working on a pollution control dam brochure. It's in progress. I think I saw Henry John's name on the list of people that are dialed in here. We're aiming to get this done sort of mid this year. It will focus on all the different aspects related to the design of these dams. But as part of that, the stuff that we're discussing here today, there will be a section in this brochure that talks about this as well and provides everyone with some guidance. So I do like for you to have a look out for that one as soon as that that becomes available to make sure you get soft copy. So very quickly then, if I can, I just want to show you an example of one of these models, because that's the sort of thing that I would have liked to see. Okay, so I'm sharing here. Make sure I share the right thing. Eh? Where is that? Sorry, everyone, just give me a moment. Oh, here we go. It's hiding at the bottom there. Okay, great. So this is an actual example of a model, which I set up just for the purposes of this discussion. So it's very, very simple, but I just want to show you how they sort of work so you get a feel for it. What you're looking at on the screen here is a network schematic representation of the system. This triangle is the dam itself. This represents the hydrology associated with the dam, which includes rainfall onto the surface of the dam and evaporation from the dam. The dam can spill through what we call this flow route or channel here. Water is pumped into the dam, and water can be pumped out of the dam. We have the ability to define. Just refresh that. To define the physical characteristics of the dam basin, the full supply level. At the moment, this dam is modeled to be 4 meters high, the starting elevation, and so on. But very importantly, also, we can model a level in this case where we say water can be pumped into the dam unless it is spilling, then the pumping will stop. But we can also pump water out of the dam to try and maintain it at a level that we are interested in, which in this case lies here. And we picked a level of 3.2 meters, which is 0.8 meters below the full supply level, just as a start to see what happens. Now, if we run the model, it's doing a daily time step analysis. The analysis in this case is 50 years long. As I said, it's just as an example to show you what it might look like. Okay, so there's the model done. And I can now have a look at the model behavior of my dam based on all of those inputs. And you can see here, what you're looking at is elevation on the y-axis and days on the x-axis. And you can see the dam being drawn down to that 3.2 level, which is the target we prescribed. But then often it would fill up and spill when it reaches the full supply level, which is this sort of, sorry, it's doing that line there. So that's the full supply level. And you can see that the dam very regularly actually reaches full supply level under this configuration, causing spills that we can go and measure here in the results. And you can see the spill events being modeled over here. So in this particular case, if this was a stochastic sequence, we could count the number of spill events, and we can classify this as a spill sequence. But quite clearly, based on this, it appears that this dam may be too small. So we can, because we now got a model set up and we can test different things, we can change, for example, the size of the dam to see how that will affect the results. So instead of a 4 meter high dam, maybe we want a 4.5 meter dam, and we want to start, we want to change this level. Sorry, where are we? This zone level from 3.2. So we still maintain that 0.8 meter difference. We want to change that from 3.2 to 3.7 to see what will happen. What I'm doing is running a program live while doing a presentation, which they say is always massively risky because something will go wrong just when you're demoing something to people. But so far it's looking good. And you can see now that the dam still, it now allows it to fill up all the way to 4.5. And we've upped this level to 3.7, but we still got lots of spill events here. So it looks like we can maybe, and I'm not going to carry on like this for much longer. I just want to show you if we, for example, said, okay, maybe it would help if we reduce this level so that pumping out of the dam happens more frequently. We can go back to the definition over here of that zone and increase it, say, from 3.7, sorry, decrease it to maybe 3 meters. And now we've got a difference there that is much larger, of 1.5 meters. Run the model. This is just to give you an idea of how that iterative process might work. So basically, I'm doing scenario analysis here to test different dam sizes and different operating levels inside that dam to see what the impact of that is on the results. And you can see now that looks a lot better. We've got the dam filling up there and there. I'll zoom in there. You can see that it fills up here almost to the 4.5. Let's see if we've got any spills. Yes, we still have 2 spills. So typically how this would work is we would do this sort of thing. So this is all based on the historical hydrology so far. So we'll run it like this. We'll do some iterations. We'll come up with a result like this one that seems reasonable. But remember, this is still based only on the historical hydrology, and we can't really quantify the probability of spill based on this yet. So what we would do then is take a given scenario like this one, and we'd run it stochastically, which I'm not going to do here because it will take too long, but we will run it stochastically in the same modeling environment, and then go back to the approach I explained earlier in the presentation to then count the spill events in each sequence, classify each sequence result as a spill sequence or not a spill sequence, count the total number of spill sequences, and based on that, we can then quantify the spill probability. And then if we still don't have the result we like, we can come all the way back to the start and try a different solution. Okay, I'm just going to go back to or maybe I should leave it here. I'm not sure. Actually, that's more or less what I wanted to cover. And I think the time looks good. So I'm happy for us to have a nice discussion about that now, Ashley, if you are as well.
All right. Thank you so much, Gerald. We already have a couple of questions.
Only easy ones, though.
And a few hands have started going up now that it's the end. So I think everyone's ready for some discussions.
Great.
There's a Q&A and there's actually quite a few questions. So one question, someone already answered it in the chat, but I'll just ask it anyway. It says, does the DWS legislation apply to maturation ponds at wastewater treatment works? And this is from Mike Shand.
Okay. What was the answer in the chat?
I'm not sure the answer in the chat was yes, because it's likely to cause pollution. So
right, makes sense.
Okay, thank you. And then next we have, okay, isn't inflow into the dam during rainfall events less when the dam is drawn down because the rainfall does not fall directly onto the water surface, but via the exposed ground where infiltration takes place?
Yeah, no, it could be. You're right. Obviously, it really depends on the size of the catchment versus the size of the dam. If the dam has a very significant size compared to the catchment, then what you're saying would be true. But there are examples, obviously, where the catchment is quite large compared to the dam itself, in which case it might not be so. That balance would be slightly different. But it really depends on the comparative sizes of these things. But a good point, yeah. Thanks.
All right. So next, maybe you can just. There's a question about something you said in the beginning. It says, can you explain the 2% spill criteria and where it comes from?
Well, that's a good question. Actually, I see Louis has his hand up, and Louis has actually, I think, a bit more insight into that because he knows some of the individuals that were involved in drafting it. Louis, can you, a 2% to me, for me personally, I think and it's a good question, why 2% per se? You could argue that it's too lenient or maybe not lenient enough, depending on what the impact of a spill event would be on the downstream environment. And that would depend also on the quality of the water that's been spilled. So, Louis, I don't know if you can maybe add to that.
Louis, your mic has been enabled, so you can just unmute yourself.
Hi, everybody, and thank you, Gerald, for that. Yeah, I actually don't have a specific answer. I think the guys that were involved, the people that actually put together the guidelines, and people like Leeuw van der Berg and so forth, that was in the section that put that together. And originally the regulations as well would be much better, but I think it's something similar to what we have in the dam safety regulations, where the people at the time that made these regulations sat around the table and was looking each other in the eye and say, okay, what would be like a appropriate level that people can still get answers for? And that shouldn't be that high, sort of, or that bigger impact if a spilling event happens. But that, yeah. So sorry that I don't actually have the specific answer here, but I know that's what happened on the dam safety side, where there's not really a scientific explanation for that.
Yeah, sorry to put you on the spot there, Louis.
No
I just want to maybe add to that. I mean, I still feel that, technically it should really be dependent on the quality of the water in that dam. But if you did bring that into the equation, it would become too complex to try and even apply it practically. So maybe it's not relevant in that sense from a practicality perspective, but I'm not sure. Thanks, Ashley.
Yeah, so mainly the 2% comes from the regulation, I guess.
Yeah.
Besides where it comes from the regulation.
Yeah, that's the thing. I'm not sure.
Okay. So the next question is, hi, Gerald, when you say that we look at our spill on a yearly basis, does this mean, number one, that if a dam spills more than once in a year, this counts as one and the year fails? Number two, or do you sum every single spill that occurs, example, dam spills 3 days in a row, and that is added to the total number of spills?
Oh, okay. The act somewhere, I think it was in the act or the guideline, I'm not sure now offhand, but somewhere they define what a spill event is. And if it spills continuously for up to 30 days, that can be counted as a single event, I think. So you can set your model up, or your interpretation of the model output, to account for that. You can see the spill days. You can then count spill events based on this sort of criteria. Continuous 30 days would be one event.
Okay. Considering that the PCD would be new infrastructure and is off-channel, where or how would you obtain the historical data?
Okay, good question. I mean, that's always a good question, not only in this context. Where do you get the data? So for starters, the things that have the biggest impact here, I mean, that's maybe the good news. The things that have the biggest impact on the dam balance would be rainfall, for starters. Now, lots of people measure rainfall. You might not have rainfall at your dam, but you might have rainfall at a station that's not too far away. And you can even do some tweaking to, maybe, if you know that your rainfall is slightly higher, whatever the case is, you can tweak that a little bit. But there's a lot of rainfall gauges in South Africa. Unfortunately, getting less so that's not ideal. But I think rainfall is not that big a problem, although you would have to acquire the data at cost if you got it from the South African Weather Service. But UKZN has a database of rainfall running up to 1999, daily rainfall. So that's also available if you can find nothing else. And then increasingly, I think it looks like satellite-based rainfall is getting better. So I think ultimately that will be the thing that we can use more readily for just about anywhere in the world, assuming that, I think the technology has a bit of growth to do, but that would be helpful. So I don't think rainfall is that big of an issue, unless maybe it's in other countries where rainfall monitoring is maybe not as good as it is here. That could be problematic. Evaporation is pretty easy. We have good evaporation data for all the quaternary catchments in the country. I've got a little database like that I can happy to share with anybody that's interested for evaporation. And then in terms of the other big impacts would be what you pump in and out of this dam, and that would be, I think, almost an outcome of your analysis, your scenario that you're trying to run. with whomever your client or the owner of the dam is. And I think those would be the four things that impact on it most. Unless there's a significant catchment area and you have to do rainfall runoff modeling, in that case, you would have to, I think, consult someone that's good at doing that sort of work to assist.
Okay.
Thanks,
The next question is, please can you expand a bit on how climate change is accounted for in the hydrology, specifically for South Africa?
Okay, so absolutely. Everything I discussed so far is based on the premise that there is no climate change. But what we can then do is we can do an entirely separate set of scenarios where we analyze everything in exactly the same way as we did before. But now we say, okay, what would happen if the long-term impact of climate change would result in an increase in rainfall of 5% and a decrease in and an increase in evaporation of 10%, for argument's sake. And we could even account for the changes in seasonality and all these sorts of things. I'll get back to where we get that from in the first place in a moment. But we can take those new hydrological baselines then, if you like, and run a climate change scenario by taking the increased rainfall and the increased evaporation and putting them back into the same model and doing stochastic analysis and post-processing the results to quantify spill probabilities. And that would then be the spill probability for that scenario, but assuming climate change impacts. The problem with all of that is, it sounds lovely, but the problem with all of that is, what does the climate change impact, in fact? So that's problematic because it's dependent on so many things. There are millions of climate change impact scenarios out there. It's dependent on the GCM that is used. It's dependent on the downscaling methodology. It's dependent on the CO2 emission scenario. So by the time you pick different combinations of those three things, you already end up with 100 scenarios. Do you see what I mean? So the challenge is to pick scenarios that maybe cover a sort of range that you feel is reasonable, that at least you can account for the possible negative impact or the possible increase in the likelihood of spill, and maybe size your dam accordingly to be more climate resilient, if you like. I think that's the right terminology. Where can you find climate change scenarios? There are websites online. For example, the World Bank, there's a World Bank-based website where you can download these impacts for suites of models based on the CO2 emission scenario that you pick. And I think they're pretty good. I can steer in the right direction afterwards if you're interested. Thanks.
All right, thank you. One last question from the chat, and then we'll move on to the raised hands. So it says, hi, I know GN 704 specifically state the sizing of water dams in mines. Can we still apply the same principles to landfills?
Oh, I don't know. It's a good question. Maybe someone else on the in the chat here knows.
Okay.
I think in principle, I would think so, but I'm not sure. Sorry, Ashley.
All right, no problem. I see Cole's hand is up. Perhaps he can answer that question. Okay.
Cole, save us. Oh, yeah.
So first of all, let me just allow Jean-Ray Thompson. You're welcome to unmute yourself and ask your question.
Oh, yeah, Gerald, thanks a lot for this. This was very interesting. I'm Jean-Ray Thompson from SRK Consulting.
Hi,
not so much a question, but rather more a comment.
Yes.
You actually did touch quite a lot on it when you were talking about the climate change. But another thing that also needs to be considered when you do these water balances is the hardening that could potentially happen in your catchments upstream, creating higher inflows into your dam. Now, I know this is specifically about mines. Mines is relatively easy to understand what type of hardening is going to happen in the catchment. But we've got a couple of clients where we are seeing quite a lot of expansion happening, and they're not taking that into account in their water balances and in their pollution control dams. And 5, 6, 7 years down the line, they are spilling every year because they are letting more water into the dam without checking the water balance and increasing their dam capacity, either by raising the wall or building a second compartment or anything like that. So that's a very, very important thing to consider, is the hardening of your catchment that could happen over time, leading to larger floods into your dam.
Yep, that makes perfect sense, John. Thanks a lot for that one.
Okay.
John, are you related to Issa Thompson at all?
That's right, yes, I'm a son.
Oh, cool. Okay, welcome.
Yeah. Then just on the landfalls, for your landfalls, you've got leachate that you extract from the bottom of the landfill that you try and take out to keep the landfill as dry as possible. And that leachate goes into a pollution control dam that needs to follow Regulation 704, even though it says it's for mining and associated industries. So the landfill would fall under that. Anywhere where you've got the potential to create harm to the environment through industrial type processes, Regulation 704 will apply there.
Okay, makes sense. Shanda, thanks a lot.
Awesome. Thank you very much.
Thank you. Louis, you can unmute yourself and ask your question or make your comment.
Thank you, Ashley. Again, Gerald, thanks a lot for your webinar and sort of good explanations. I also just want to make a sort of a comment or highlight some important things or one specific important things that you maybe not spend that much time on when you were explaining this water balancing, is the importance actually of your maximum operating level. And it comes back to what Jandre just said as well. So I think a lot of people think you do a once-off water balance and then you've ticked the box and everything is okay. But you actually, that's why you made the point about the monitoring. Okay, in the beginning, when you design the dam, and if it's a new PCD, you'll have to do some modeling and some theoretical calcs and things like that. But then after that, it is actually very important to consider to do monitoring, to get the actual sort of behavior of the processes that you deal with, and then consider whether you need to change your maximum operating level or not, and change your and each maximum operating level is actually if you determine a maximum operating level, it is directly related to the processes. So if anything changes, you need to change your maximum operating level, otherwise your exceedance probability of spillage will change.
Yeah, that's exactly right, Louis. Thanks.
All right, thank you, Louis. Cole, you can unmute yourself and ask your question or make your comment.
I think I'd first like to thank Gerald a lot for doing this presentation and being willing to do it, because I think it is something that's exceptionally important, and it is something that we do see lacking quite often in licenses when they come, whether they be from a waste management mining license or from a water use licensing perspective.
Yeah, you're welcome, Cole.
I think maybe look, I wasn't around when the in the DWS when the regulations, etc., or the guidelines were written. But I just want to sort of clarify for those in attendance that ultimately we see any spillage, or let's put it this way, the Act says that any spill to the environment, if it's dirty, is considered a spillage, right? So strictly speaking, it's not allowed to occur. And when it does occur, it needs to be reported and addressed as an incident and dealt with it in terms of the regulations that deal with incidents, etc. However, when it comes to mining, where predominantly those guidelines were set up for, typically we recognize that the level of risk associated with that particular waste, if we look in terms of the NEMA regulations 2013 specifically, the majority of mine waste ends up being a type 3 waste requiring a class C form of containment. But I'm talking about the risk associated with. So I think the department also recognizes that although we don't want spillages, it would be wholly unreasonable for us to say, okay, guys, go design a PCD for a mine to not spill ever. In other words, if you had to take it to normal dam engineering, say for a SEF event type of thing, we know that's wholly unreasonable, and the amount of money that would need to go into that would be astronomical. So there has to be an acceptable level of risk and recurrence to which we requesting applicants, license applicants, and mine owners, and whoever it is that are having these pollution control dams to actually size their facility for. Now, that's sort of my understanding of historically where it's coming from. And maybe to touch on the question about the landfills is if you take it a step further, when we're looking at municipal solid waste and Class B facilities, the sizing requirements typically that we're looking for is exactly the same as those for mining, size to not spill more than once in a 50-year period. However, if you're looking at a hazardous landfill or waste disposal facility, the risk associated with such a spillage is obviously even more to the environment and persons. So there also, even more so, we would not like that pollution control dam or the separate leachate dam, if they are separate, to spill ever, quite honestly. But once again, we also can't ask developers and owners and those persons to size it to such a level of non-spillage, if I can call it that. Sorry, I'm losing my English here a little bit.
No, it makes sense, Carl. Thanks.
But yeah, so effectively, at the end of the day, we would say, okay, an acceptable level of spillage or risk of spillage being occurring once in a 100-year period, or no more than once in a 100 period on average for a hazardous waste facility, is typically what we are adjudicating on when we're looking at waste management licenses or water use licenses for hazardous waste facilities. So I thought maybe I could just add that, and maybe it gives a little bit of clarity of what we effectively dealing with or adjudicating on when it comes time that it's actually coming across our desk for license applications.
Great, thanks for that, Carl.
Thank you so much. I really appreciate that comment, Carl. Can I please just ask a few more questions? So we've got a few more in the question and answer section. Number one is from Alan Chamoli. He's asking, the regulations that we are discussing were promulgated in 1999. We are some 35 to 36 years down the line. Should the 1 in 50-year recurrence interval not be researched and or confirmed or updated?
And I agree. It's a good point. And the sort of things that Carl mentioned just now, I think these sorts of things need to be taken into consideration. I think there's definitely scope for research and involving the important role players like DWS. Carl, I'm sure you would agree.
All right. Another question is, how is silt inflow, example erosion upstream, catered for in the model?
Okay, so a great question. Thank you. Maybe to explain the model that we would set up, you can set it up to do whatever you like. So if sediment is significant, you can set the model up to account for that. If it's not, then you don't. The model is completely scalable and applicable to more or less any situation. And if there's something in particular that the model can't handle, then we can add functionalities to the model to cater for that sort of situation. So in principle, that's not a problem at all. I mean, technically, you can do the modeling in a spreadsheet if you really wanted to, but there's just many disadvantages to that. So that's why we like using a model like the one I showed you. But certainly, if that was an issue in a particular case, we could set up the model or a scenario in the model to account for that explicitly. Yes. But it wasn't so in my example. I wanted to keep it simple, just to show you what it looks like. But definitely, yes.
All right, thank you. DeAndre Pillay, your question's already been answered now. So it's saying, hi Gerald, thank you for the informative presentation. If a dam has been previously sized, where data older than 20 years has been used, should more than one spill event occur in 50 years, how do we motivate that the dam was accordingly sized before climate change altered rainfall patterns so drastically?
Okay, if your question relates specifically to climate change, I haven't really seen in my many days of looking at rainfall data across the country any observable impact on rainfall. It might be different for evaporation, but I haven't seen much of it yet. I'm not saying it's not coming, but I feel that if you use rainfall data, let's say the rainfall period, the data period that you used is adequate. Let's say you used 50, 60, 70 years of data. Even if the data stopped 20 years ago, I still think it would be valid, assuming that you then take that and do stochastic analysis, like we've said. I think it would still be valid. If you never did the stochastic analysis in the first place, then that's a different discussion. But I don't feel that the impact of climate change is at least in the data sets that I've seen. I look at a lot of rainfall data all the time. I haven't really seen any change, any noticeable movement in the statistical characteristics of the data sets so far. I'm not saying it's not there, but I haven't seen that locally. I have spoken to people more on an international basis that say they've seen that in Germany and Canada and whatever, but I haven't really seen it here.
Thank you. Yeah, our time is coming close to an end. So I just want to, maybe this is an important question. Louis is asking, do you have to pay to use the website waterbalance.co.za?
Thanks, Lee. Good, excellent question. So the answer is no. We have developed this model as a generic model to be able to do water balance analyses, like I just showed you, or to do yield analysis, or to do operational analyses, whatever. The basic model would be made available. All you need to do is to register with us, and we would make use of the basic modeling features available to you free of charge, in which case you can do many things with it already. If you want to use specialized services, then that would come at some cost. But the costs, even if you take the full suite of things, would be an order of magnitude smaller than comparative models available from other international organizations. So yeah, thanks for that question. Actually, I wanted to mention to everybody and to you as well, as SANCOLD, we from time to time host training courses for the greater good of our community. And I wanted to ask whether there would be interest in a training course on this sort of thing. That would
Perhaps
include,
perhaps people can raise some hands and give some reactions. There seems to be a lot of hearts and claps and yes, pleases. Yes. So Cole, you can unmute yourself if you want to comment on that. There's a lot of hands going up, so everyone is saying yes, and you are welcome to discuss that with me, and I'll get the right people in contact.
No, actually, I'll just say yes, definitely. I think the industry and even the youngsters in the department could really get a lot of value from such a training exercise. So Gerald, I definitely think it's something to pursue.
Oh, fantastic. Okay, and what we'll do then is, if we have a training course like this and everybody attends, then we could also register all of the attendees as users on the website.
All right, fantastic. That sounds amazing. Thank you so much, Gerald. This was an extremely insightful presentation and discussion, and I think that nobody left here without learning something. Wonderful. And I'm hoping that they're going to share the recording far and wide as well, and just to get the word out there and just to help a few people with this regulation and how to comply to it. And thank you so much for your time. I really appreciate that you did this free of charge and out of the goodness of your heart for the SANCOLD YPF, and this reaches a much wider audience than what you know, and we're just so thankful that you've come out today. All right.
Thank you, Ashley, for the opportunity. It's always my pleasure. Thanks.
Great stuff. If you are still in the audience and you need some help with this, please contact Gerald. He obviously works in this field and would be the expert in doing this type of work for you if you need it at your company. All right, I'm going to take 5 seconds of your time just to encourage you to please register as a member of SANCOLD if you have not yet done so. This is how you will get access to some of those reports that Gerald was talking about, and it also helps you with your CPD points if you're a registered engineer with EXA. And there are many other benefits. If you want to get to know what all those benefits are, you can also follow the SANCOLD YPF page on LinkedIn. It is not exclusive to YPF. Anyone can join. That is just, at the moment, the YPF drives that page and is sharing the information. So thank you everyone for joining. Your time is also valuable to us, and it really makes it a great success if you are paying attention and taking part and joining. And at the end of the year, it's nice just to look at the stats and to know who we reached and who was helped. So thank you for joining and for taking the time. I really hope that it was valuable and that we will see you at the next webinar. Have a good evening, everyone.